we talked about bonding, and we talked really about ionic bonding first here, and we talked about using Lewis structures to illustrate ionic bonding. And as we talked about a number of times earlier, really the whole basis of bonding is for everybody to get to the same electron configuration as the noble gases. Remember, when we talk about people sort of getting to the same electron configuration as the noble gases, we're not talking about the elements changing. It's just the electrons within those elements are changing. Remember, in order to change the element, you would have to change the protons, and we're not doing anything with the protons here. We're just doing with the electrons. So they are the same elements, but they do just end up with the same electrons as a noble gas, which ultimately makes them pretty stable, and really what the goal of everybody's trying to do here. So we're going to now talk about sort of covalent bonding. If there wasn't no questions on what we just finished up, everybody's good? Okay. So let's get into covalent bonding. Covalent bonding is different than ionic bonding. And as we touched upon earlier today, it is covalent bonding that really happens between two nonmetals. So as we talked about up on the periodic table, all the nonmetals are pretty much in the same location. If you need to move, go ahead and move. This is the worst room for lecturing. You know, last semester we did both in here, lecture and lab, so it was really bad. But it is between two nonmetals, and because they are really in the same location on the periodic table, they do share, like we talked about, very similar periodic trends, which ultimately means everybody wants to hang on to their electrons in this situation. So the best that they could do is they're going to sort of agree upon, if you will, to some aspect of sharing is going to happen. And as we'll talk about, that sharing may be equal sharing, maybe unequal sharing, but even in sort of an unequal sharing situation, there is the aspect of sharing. So we're not going to get a transfer of electrons like we talked about in ionic compounds here. We're going to get sharing of electrons that occur. So if we look at something like Gilbert Lewis sort of illustrated the role of electrons in bonding, hence why we call it Lewis structures and Lewis dot symbols. Hydrogen has one valence electron because frankly, it only has one electron total. So that's the valence electrons. So in this situation, obviously, if we have two hydrogens, what's going to happen in this case is they're just going to kind of come together and share those electrons, which we could represent, as we see here, with a couple of dots. Or we could also represent bonding here and sharing of electrons with a line. A line does represent two dots or two electrons that are being shared. When we look at each of the hydrogens in this bond, the two electrons in the middle that are being shared do count for the guy on the left. They also count for the one on the right. So in this particular situation, hydrogen is sharing basically a pair of electrons between each other. That technically gives hydrogen two electrons, which is not bad, because if we look on the periodic table, the element that comes after hydrogen is helium. And helium is a noble gas, and it has two. So hydrogen, and one important thing to remember when we talk about bonding is hydrogen only needs two electrons. It only needs to basically get to a situation where it basically achieves two electrons through sharing, and that is able to move hydrogen really to helium, and it becomes a noble gas configuration and very stable. So as we go through it, hydrogen pretty much should always look like this. Basically a line to hydrogen, two dots to hydrogen. Hydrogen should never have 8 dots around it because it is definitely wrong, and you should mark it yourself. So never in the future, as we start talking, draw hydrogen like this, because that's definitely wrong. So really just two electrons, because it just needs to get there to helium. Now, one line does represent a single bond or two electrons. Two lines represent a double bond or a sharing of 4 electrons, and 3 lines when we do covalent bonding represents 6 electrons, or what is referred to as a triple bond. And again, all those electrons are needed. In some cases, you just need a single bond to get everybody to 8, if you will. In other cases, in order to get everybody happy in that noble gas configuration, you need to make some double bonds or triple bonds basically to achieve that sort of goal. Now, in a covalent bond, it's basically the attraction to both of the nucleuses that basically hold that together. So in the case of something like hydrogen, you know, though you can think of the nucleus kind of here, if you will, the electrons here are attracted to this side. They're also attracted to this side. And it's kind of that dual attraction that kind of locks everybody into place in terms of the bond that's happening. Again, here, there's absolutely no transfer of electrons. There is sharing of electrons, and that mutual opposite attraction to the nucleus kind of locking everybody into that bond. Even though the electrons are negatively charged, they don't really want to be near each other, but they sort of are in that sense because of that positive charge of the nucleus. We look at another example like fluorine. Fluorine is, again, our group 7, which means it has 7 valence electrons. And obviously another fluorine would also have 7 valence electrons. In this case, because they are both fluorine, they have absolutely identical periodic trends, which means neither one of them is going to give up that electron. The result of that is we will form a bond here between the fluorine, where those electrons are now being shared. And when we look at fluorine on the left here, by sharing those electrons in the middle, it's able to achieve 8 electrons. The fluorine on the right, also sharing those electrons in the middle, are also able to achieve 8 electrons. That puts everybody here in terms of fluorine to 8 electrons, which puts everybody in terms of the periodic table into the same electron configuration as our group 8. 8 obviously is a super important number in bonding. It's what's known as the octet rule, as we'll talk about. And again, basically that's going to allow everybody to get to that electron configuration like our noble gases. Any questions on that there? Now, when we look at this, there are several different types of electrons that we see in this picture here. The electrons that are the dots on the outside, those are what are referred to as lone pairs, are non-bonding electrons. Most books nowadays call them non-bonding electrons, but if I say lone pairs, then obviously it's the same thing. There's also the electrons in the middle. These are electrons that are involved in bonding, and these are what are referred to as bonding electrons. So non-bonding electrons or lone pairs, much like the name implies, are electrons that are not involved in a bond. We know that because when we look at all these electrons here, there's no other element written next to it. So it's not involved in bond. The bonding electrons are the ones that are really being shared between 2 atoms. And whenever you draw Lewis structures, as we'll talk about, you should always include all those electrons, the bonding and the non-bonding electrons. It is the bonding electrons that are typically drawn with a line, but if you want, you can do them as dots. So like we saw earlier, if you want to, draw this guy like this with all dots, technically is not wrong. But most people will sort of turn those bonding electrons into lines when they do draw Lewis structures, but you can do all dots if you like. Any questions on that there? Now, a Lewis structure is a representation of covalent bonding, just sort of like we used it with ionic bonding. Also different, though, again, because there is no transfer of electrons here, we do not show any charges when we have a covalent bond because there really kind of is no charge because there's no transfer of electrons. So we don't do any charges or anything like that when 2 nonmetals come together. It is only the valence electrons that are shown in our Lewis structures. Again, there have a lot more electrons, each of these atoms, but those are the core electrons, and it's only those valence electrons which are involved in bonding. So if we look at water, if we draw the Lewis structure for water, it looks something like this. And again, in this situation, in this case, oxygen needs to share an electron with each of the hydrogens. So by doing so, it's able to achieve 8 valence electrons. And then we see each of our hydrogens by sharing one electron with the oxygen, are also able to achieve what they need, which is only 2 electrons for everybody to achieve that noble gas configuration. So covalent bonding, sharing electrons, that is how they achieve that configuration. And again, the ultimate goal of bonding is to get everybody there. So clearly, as we talked about, a couple of really important rules in bonding is the octet rule. Pretty much everybody will continue to make bonds until they have 8 valence electrons around them. And in this case, everybody really, except for hydrogen, as we talked about, hydrogen should only have 2, and that will get it to helium. That is sometimes referred to as the duet rule for 2. So hydrogen, as we talked about earlier, pretty much if you're drawing a Lewis structure, should look like that, should have no dots around it, and should always be on the outside. You should never have hydrogen in the middle, because then it's going to have way more than 2 electrons. So hydrogen should always be on the outside, no dots, just like that. Everybody else pretty much going to keep going until they get those 8. And like I said before, sometimes that may just require single bonds to do that, and sometimes it may require double bonds or triple bonds. And we're going to talk about the situations in which you should do a double bond or a triple bond. And the situation is you should not just start double bonding and triple bonding things out of the box. You should actually save that problem of double bonding and triple bonding to sort of fix an issue where you maybe come up short on electrons. And that usually will get you the correct sort of picture. So let's talk a little bit more about some of these bonds that we do see in these Lewis structures. As I mentioned before, a single bond is the sharing of 2 electrons or 1 pair of electrons. And again, you could use a line to represent the sharing, or you could use obviously 2 dots to represent sharing, like we saw in F2. A double bond occurs when we have basically 2 pairs of electrons or 4 total electrons. And so, for example, something like CO2, in order for it to be really happy, in order for it to reach sort of that stable configuration, it actually needs to make 2 double bonds in it to get there. And by doing so, what we see is the oxygen on the left by double bonding gets to 8 electrons. The oxygen on the right also by double bonding gets to 8 electrons. And then our carbon, by making those 2 double bonds, able to get to 8 electrons. So as I said, sometimes it requires 1 double bond, maybe 2, sometimes it requires a triple bond to get there. But the goal of making these extra bonds really, again, is the same goal, to get everybody to that stable configuration of 8. Lastly, obviously, as I mentioned, you can do a triple bond, which would result in a sharing of 6 electrons or 3 electron pairs. And here's a couple of examples of a triple bond. Nitrogen is an example. Nitrogen needs to keep making bonds until it hits a triple bond. When it does so, that's going to allow each of the nitrogens there to share the 6 electrons that are in the middle. So they count for the nitrogen on the left, they count for the nitrogen on the right. And by doing so, that gets everybody there are 8 electrons. And obviously our carbon on the bottom very commonly can triple bond with another carbon to get us there. Again, we still see what we talked about with hydrogen, only 2 electrons on the bottom there. Again, looking like I showed you just a second ago, on the outside, 1 line drawn to it. So it's a good thing to keep in mind. I can't tell you how many people like to put dots around hydrogen like all day, all around. Also, hydrogen will never double bond or triple bond for the same reason. It would have way too many electrons. So those are common mistakes that people make. I've seen a triple bond to hydrogen with dots, and that's like way too many electrons for sure. So don't get creative with hydrogen. It's just 1. So what determines whether or not electrons are going to be shared, or how they're going to be shared? Are they going to be shared equally or unequally? It really is electronegativity, as we talked about earlier today, which is really the ability of an atom to bring electrons towards itself. So if you remember, we talked about the periodic trend. We'll see it here again. Again, it increases as we go up and to the right, and it decreases as we go down, with fluorine being the most electronegative element we could have. And it is really what determines whether or not electrons will be shared equally between the 2 atoms. Will it be shared unequally? And you could even use it to determine, would you expect the electrons actually to be transferred? Is the electronegativity. When we look at something like hydrogen, clearly in this particular case, we have two hydrogens that have come together. They are both hydrogen, which means these electrons we would assume would be shared equally between them, as the hydrogen on the left is pretty much identical to the hydrogen on the right, which means they both are going to have the same pool of those electrons to each other, and we would result in an equal sharing of electrons. Same deal as we would expect with F2 that we saw earlier. Again, they are both fluorine, which means they both have the exact same pool on those electrons. That's going to result in those electrons really spending about the same amount of time between them and them being shared equally. The result of electrons being shared equally is what is referred to as a nonpolar covalent bond, which most people will just shorten to a nonpolar bond. So a nonpolar bond is one where we get the electrons being shared between two atoms equally. The way you could kind of think of a nonpolar bond is because they're being shared equally, we have equal distribution of electrons over the whole atom, and we basically have sort of a neutral atom, if you will, a neutral bond, if you will. There's no side that's more positive, there's no side that's more negative. Because of that equal sharing of electrons, that bond is relatively neutral in a sense, because we have the perfect equal sharing of electrons. By the way, we do get perfect equal sharing of electrons when we have two of the same elements, like here. That is as perfect of sharing as you could get between two things. Does a nonpolar bond always have to be two of the same element? No, you could have two different elements that can result in a nonpolar bond. And there are some degrees of equal sharing, as we'll talk about here as we go through electronegativity. So what happens though if we take something like hydrogen and fluorine and put those guys together? When we've put hydrogen and fluorine together, in this case, we no longer have two of the same elements. We also have elements that are on different sides of the periodic table. Between hydrogen and fluorine, which one would be more electronegative? It would be fluorine, since it is the most electronegative you could have. So what that means in this particular case is those electrons that are being shared between hydrogen and fluorine will no longer be shared equally, and they would be more attracted to the fluorine side. So what we would have is a really bad drawing here of my really bad lines is like my electrons moving that way, and we would have just a little bit of guys still hanging on over there. The result of that is a wonderful artwork, but the result of that is it's going to create on the fluorine side, is it going to be more positive or negative as the electrons go towards fluorine? It's going to be more negative. It's going to create what is referred to as a partial negative charge. That's a delta symbol with a negative. So that's a partial negative charge. The result of the electrons basically moving away from the hydrogen is it's going to be a little bit more electron deficient, and it's going to be a little bit more positive on that side. And we get what is referred to as a partial positive charge that occurs here on our HF. This type of bond where we get unequal sharing of electrons is what is referred to as a polar covalent bond, or most people just lay up a polar bond, assume that it's covalent, so most people just call it a polar bond. This can also be represented, as we will see, by the use of what is referred to as a dipole arrow, and that is an arrow that points to the side that's more negative. So this arrow, when you see these dipole arrows, these are sometimes referred to as dipole arrows, and they always point to the side that's more negative. And this part of the arrow, which kind of makes like a plus sign, is to the side that's more positive. And that is basically the representation of that. So in a polar bond, we have unequal sharing of electrons, resulting in a side of the bond that's more positive and a side that is more negative. Why is it only a partial negative charge and a partial positive charge? Why is it not a full positive charge and a full negative charge? It would be ionic. In an ionic bond, it is a transfer of electrons. Electrons completely go from the metal to the non-metal, resulting in a complete positive charge and a negative charge. In a covalent bond or a polar covalent bond, what we have here is still sharing of electrons, even though it's not equal and the hydrogen is barely hanging on over here. He is still hanging on to those electrons, so it hasn't fully transferred. So we get what we refer to as partially negative charge, partially positive charges, because we still have an aspect of sharing occurring here, and we haven't had a full transfer of electrons that have occurred. Any questions on that there? Yeah. It is. Yeah, go ahead. Not necessarily electronegativity on that. That's going to be more basic of, did we get to the octet rule? Did everybody get to 8? And they will continue to make those bonds until they do get to that. And that's really more sort of determined. Really, electronegativity, as we'll talk about here in just a second, using electronegativity is really the thing that we use to decide if I take this atom of this element and this atom of this element and I put them together, would I expect there to be sharing of electrons? Would I expect there to be transfer of electrons? And if there are sharing of electrons, do I expect it to be equal sharing or unequal sharing of electrons? So it's really the electronegativity. And honestly, you really don't even need it for ionic bond, because simply if you have a metal and a non-metal, it's ionic. You don't have to worry about the electronegativity. But really, when you're dealing with two non-metal atoms that come together, we really use electronegativity to help us decide in between just those two atoms, will those electrons be shared equally or unequally? Other questions? All right. So I think that's what I just scribbled here. So again, that HF is held together by the sharing of electrons, referred to as a polar bond. That's pretty much what we just talked about on the previous slide. And much mirror type of thing there with our electron density. So there really is sort of, up at this point, kind of, if you want to think about it, 3 different types of bonding that we sort of talked about. There's ionic bonding, there's covalent bonding, which is really made up of 2 types, a nonpolar bond and a polar bond, which is some type of sharing of electrons. So you could think of it like, on one end of the extreme, we have an ionic bond. And that is always between a metal and a non-metal, where we have that transfer of electrons like we talked about, resulting in a cation, which is positively charged, an anion, which is negatively charged. Absolutely no sharing of electrons there. Complete transfer of electrons. So something like sodium chloride would be an example of that. On sort of the other end of the extreme, we have a nonpolar covalent bond, which is between 2 nonmetals, and it is equal sharing of electrons, like, for example, the F2, the H2 that we talked about. We have nice equal sharing of electrons. And sort of in the middle is a polar covalent bond, also between 2 nonmetals, also sharing of electrons, but unequal sharing of electrons. And an example obviously would be the guy in the middle there, HF, where we do get this separation of charge that occurs between the 2 guys, and we get a side that's more positive and a side that is more negative within that bond. So one end of the extreme on ionic, we get a complete transfer of electrons always occurring between metal and non-metal. Other end of the extreme, perfect, I won't say perfect, but equal sharing of electron is a non-polar covalent bond. And in the middle, we have not so much of, I'm going to lose my electrons or transfer my electrons, but not so equal. So some degree of unequal sharing occurring. Obviously, anything that involves covalent bonds, always 2 nonmetals, and anything that involves Ionic, pretty much a metal and a non-metal. There is sort of an example of a nonpolar bond, which sometimes people will refer to as a pure covalent bond. And that really is like a nonpolar bond. A pure covalent bond is something like H2 and F2, where you basically have perfect equal sharing of electrons. So it's still considered a nonpolar bond, but some books will classify it as like, this is a pure covalent bond. It's like the perfect equal sharing of electrons you could have. It does not. So we'll talk. So for example, you could have a bond between carbon and hydrogen. It's considered nonpolar. And so you could definitely have some bonds between different elements that will result in an equal sharing of electrons. We're going to talk about that in about 2 slides, I think. So there's actually some electronegativity values that you use to help you determine that exact question of, would you expect it to be equal or unequal sharing of electrons? Other questions? Okay. So let us get into really how to determine that. And it really, again, as I mentioned before, is the electronegativity. That really is what you want to look at, especially if you're dealing with a covalent bond between 2 nonmetals. You want to look at electronegativity to help you decide the question of, are we going to get equal sharing or unequal sharing? One thing for sure, you will get equal sharing if it's two metals that are the same element together, like H2 and F2, they're always going to be nonpolar because we'll always have the same sharing of electrons that's going to occur. But when we do get into some different elements that come together, some different nonmetals that come together, we do want to look at electronegativity to help us decide that. So as we talked about before, the general trend on the periodic table, up to the right, more electronegative, down and left, less electronegative. And that really is based on a couple of those periodic trends that we talked about, electron affinity and ionization energy. Remember, as we talked about, up and to the right, pretty much everybody's small, they're hanging on to their electrons, and they much rather grab electrons than lose electrons. When we go left and down on the periodic table, we got guys that are larger, not really interested in hanging on to their electrons, and not really interested in really gaining electrons, so that they want to really release those electrons. So a guy by the name of Pauling actually came up with a numbered system that we can use to help us calculate whether or not, when we put 2 nonmetals together, will we achieve sort of a polar bond or a non-polar bond, equal sharing or unequal sharing of electrons. And his sort of calculations go from a value of 0, which is not electronegative, to basically a value of 4, which is the most electronegative. So something like fluorine will have a value of 4. And you can do it. We do really a simple math calculation. We take the 2 elements that are involved in the bond, we take their electronegativity values, and we basically just subtract them. So we just subtract the 2 electronegativity values, sometimes referred to as delta En, change in electronegativity. You basically just subtract the 2 values. And depending on the value that you get, it will give you an indication of whether or not you would expect that bond to share electrons equally or share electrons unequally. So let's take a look at that. So this is Pauling's table. And before we do, let's go back here. The difference in electronegativity value when we do that, if we get anywhere from 0 to 4, 0, not to 4, try again. 0 to point, it's a Monday. I'm just going to keep scratching this way. That's what. All right, let's try that again. 0 to 0.4. There we go. That is considered a nonpolar bond. So anything where you have a difference in electronegativity from 0 to 0.4 is considered nonpolar. I'll go up on top because I know it's hard to see low here. Anything from like 0.5 to just below 2 is considered a polar bond. And anything that is basically a difference in electronegativity of above 2 is considered ionic. So difference in electronegativity where we get 0 to 0.4 is considered nonpolar, which means equal sharing of electrons. Anything above 0.4, so 0.5 and on, below 2 is considered a polar bond, which means unequal sharing of electrons. And typically anything above 2 is considered ionic, which means no sharing of electrons, transfer of electrons. Again, really, do you need this guy here? The answer is no, you really don't, because as soon as you see metal and non-metal, it's ionic, no sharing of electrons, transfer of electrons, and you'll be good. But again, the other one you can use to help you out there. We talked about earlier the idea that sometimes people will classify it as a pure covalent bond, and that usually is a difference in electronegativity of 0. So if you have a difference of 0, that is usually considered a pure covalent bond, perfect equal sharing of electrons, like we would expect with obviously H2 and I2. So if we look here at this table, this is a table of electronegativity values, and we see our general trend as we hit over here to fluorine, which is 4. If you go left and down to right about there, that is 0.7, which is a much smaller number. And we could use this to help us determine, what we would expect. So for example, if we did our sodium chloride, we would look at sodium, which is 0.9. We would look at chlorine, which is 3. And we could take the difference in electronegativity, which would be 3 minus 0.9, gives us a 2.1. 2.1 is above 2, which we would expect it to then be ionic. Really don't need those numbers, because as soon as I see sodium and chlorine, that's a metal, non-metal. I know it's ionic. Is it perfect, that 2 number? It's not. There are some combinations of metals and non-metals that will give you a difference in electronegativity value less than 2, but it's still ionic and you'll still get a transfer. So best for ionic bonds, just to remember, metal, non-metal, ionic bond, transfer of electrons. Don't even bother with the electronegativity value. You should be good in most cases. Earlier, we also looked at F2, right, which obviously has a electronegativity value of 4 and 4, which means when we take the difference in electronegativity, that is 4 minus 4, which is 0. That definitely is a non-polar bond, or a pure covalent bond in this case, because it is a difference of 0. That is definitely equal sharing of electrons. If we look at our HF that we did earlier, H is 2.1, fluorine is 4. When we do the difference in electronegativity, that is 4 minus 2.1. That is like a 1.9. 1.9 is just below 2, and it is in that polar region. And we would expect this to be a polar bond. And that does make sense, right? It is still sharing of electrons, but in this case, who really has most of the electrons is fluorine, right? It's really pulling those electrons much closer to the fluorine side than the hydrogen. And we're almost to a point where we're going to get those electrons to transfer, but they haven't completely transferred. Hydrogen is still barely hanging on in that case. What number should you do? You should do larger minus small and take a positive number, when you subtract them. Question on that there. Yeah. They would be given to you. They would be given to you in a problem if you needed them. If you didn't need them, or they weren't given to you, I guess, you could use the general trend in electronegativity to help you answer it. So up and to the right, more electronegative, and left and down. In most cases, just using that sort of trend is probably a quick way and easy way to figure it out. And I would say in most cases, you would be correct probably in your assumption based on that. So why don't we do some here just to make sure. Let us, so why don't you do, let's do carbon and hydrogen. Let's do carbon and sulfur. Let's do nitrogen and oxygen. Let's do potassium and phosphorus. Let's do oxygen and sulfur. And lastly, let us do carbon and sulfur. So for each of these, use the electronegativity values to determine Is it ionic? Is it polar? Or is it a non-polar bond? So needed them. So we just want to look up the values. So carbon is 2.5. Hydrogen is 2.1, which means when we take the difference in electronegativity, 2.5 minus 2.1 gives us 0.4. 0.4 is our cutoff, right, for a polar bond in this case. That is really why the cutoff is at 0.4. Carbon, hydrogen is the basis of organic chemistry, and pretty much all organic guys are non-polar for the most part, and that's why we actually go up to 0.4 for our cutoff. Any questions on that one there? If we look at nitrogen, nitrogen is 3, oxygen is 3.5. Again, taking the difference here gives us 3.5 minus 3. That is going to give us a 0.5 difference. And that also would be, I'm sorry, did I say polar? I meant to say I think I said non-polar. I think I wrote polar. Sorry. That should be non-polar for CH. Just make sure, because 0.4 is our cutoff for non-polar. But 0.5 is above, obviously, 0.4. So that should be polar in this case. So yeah, definitely CH is a non-polar bond. And our 0.5 there gets us above there for our NO, which would be polar in this case. If we look at potassium, potassium is 0.8. Phosphorus is 2.1. So if we take our difference here in electronegativity, it's going to be 2.1 minus 0.8. And that is going to give us a 1.3 in this case, right? And in this particular case, that is definitely below 2, but it is still going to be ionic because it is a metal and a non-metal together. So this is an example, as I was talking about earlier, that you definitely can have a metal and a non-metal that gets you something less than 2, but it's still going to be ionic. And that's all really you have to refer to is basically a metal and non-metal. Oxygen and sulfur, in this case, oxygen is 3.5 and sulfur in this case is 2.5. And this would obviously give us a difference of 1. And that is going to give us a polar bond. Any questions so far on that there? Carbon, which is 2.5. Sulfur, which is 2.5, actually gives us a difference in this case of 0 when we subtract the 2. That means actually the bond between carbon and sulfur is non-polar. And that is an example of 2 different elements that obviously will share electrons equally. There is a relationship on the periodic table, these two. Carbon and sulfur are what we like to call diagonal of each other. One is further up, one is further to the right. They kind of cancel out their differences, and we get this diagonal relationship. You also see it with nitrogen and chlorine, right? Also diagonal of each other. You have basically the same electronegativity value. There's a couple of places throughout where you'll get the sort of diagonal relationship where one may be further up, but one may be further to the right. And they basically will cancel out their differences in terms of electronegativity and actually will end up giving you a non-polar bond. Question on that there? Yeah. Yeah. Yeah, so we actually have 2 examples here where we really didn't need the table to help us with. And that would be examples where we go backwards, hopefully. Maybe. Up. There we go. All right. So where we have this guy, for example, right here, nitrogen and oxygen, we look at the location of nitrogen and oxygen. This is nitrogen, this is oxygen, right? They're in the same row on the periodic table, which based on just our natural knowledge of the trend of electronegativity, which one should be more electronegative? It should be the oxygen, right? It's further to the right. They're in the same row. So you wouldn't even actually need this table just by looking at them being in the same row. You know that really the oxygen should be more electronegative, and there will be a big enough difference that it will result in a polar bond. Also, if you look at our oxygen and sulfur, this guy. Oxygen is here and sulfur is here. They're in the same group, right? And what we know about electronegativity in group is increases as you go up. So we would know just by the placement of those two being in the same group that oxygen should be more electronegative than sulfur, which is what we see with the numbers. And that should also give you a polar bond. So you absolutely don't need this table if you're comparing two elements that are either in the same row. And if they are in the same row, the one further to the right would be more electronegative and would result in a polar bond. Or if they're in the same group, the one further up in the group would be more electronegative, and that would be a polar bond as well. And obviously, whichever one's more electronegative would be technically the way the arrow would be pointing, and that would be where it'd be more negative on that element, and it would be holding the electrons. So those are definitely two situations, and they do occur a lot, where you end up with two guys in the same row or group, and you could just simply use the generic trend and you'll be in good shape. Even if they're really sort of not in the same group or row, as long as they're not really one of those diagonal ones, you know, you could almost still use the trend and probably make a pretty educated guess if you don't have the numbers, you know, with other on that. Okay. So like I said, it would be provided for you if you needed it. Otherwise, I would assume you could do it, like I said, just based off of the general trend in electronegativity. Obviously, as we saw, atoms with widely different electronegativity values will typically give up their electrons and form ionic bonds, and that's really your metal and non-metal. And as we talked about, and as we saw in that example that I picked, not every combination of metal and non-metal will get you over that 2 number. It is just sort of a relative number, and there are obviously several exceptions. So for ionic, as we talked about a number of times, metal, non-metal is pretty much all you need to worry about on that. Guys with very similar electronegativities will form some type of covalent bond where we'll have sharing of electrons. And again, as we talked about, pretty much all the non-metals are like cordoned off there in the same spot on the periodic table, which means, again, the best they're going to do with each other is some aspect of sharing, which may be equal or may be unequal. And that's what leads us to what we know, that the metal and the non-metal will get us our ionic bond, and our 2 non-metals will obviously get us our covalent bonds. All right, so those are sort of the rules that we talked about. And again, that 2 number, just a relative cutoff for ionic. Sometimes people will refer to this in terms of bonding as percent ionic character. If something is 100% ionic, it basically is an ionic bond. If it has 0% ionic character, it basically is a covalent bond or a pure covalent bond. And obviously some degree in the middle would result in some type of polar bond that would occur. All right, any questions on how we determine electrons being shared equally or unequally? By the way, what we were just talking about with electronegativity, as I mentioned, is really what you look at in terms of determining how the electrons would be shared. That is what is sometimes referred to as bond polarity. So when somebody talks about bond polarity, they're talking about using the electronegativity values to determine whether or not those electrons would be shared equally. And when we talk about this being a polar bond or a non-polar bond, we're not talking necessarily about the entire molecule as a whole. We're simply talking about between these 2 elements, how those electrons are being shared. We will see later on that you could have a molecule where you have unequal sharing of electrons, but overall, with everything into consideration, actually does share the electrons equally as a whole and is a non-polar molecule. So there's 2 types of polarity that we talk about. What we just talked about is referred to as bond polarity. When we talk about taking all the bonds into account in a molecule and the molecule as a whole, that is what is referred to as molecular polarity, which we'll talk about at the end of this chapter. So keep that in mind. Sometimes people get those 2 things confused. So now we've seen all these drawings. Let's talk about really the steps that you should follow to draw Lewis structures. And if you follow these steps, you should end up with pretty much a pretty good structure. If you don't follow these steps and you just try to do it by piecework, which is a very common thing, by piecework means everybody draws the dot structures with their electrons, try to figure out where the electrons go, how they make the bonds, you will end up with the wrong structure. You'll end up with too many bonds, too many electrons, not enough electrons. But if you follow these steps, you should pretty much end up with a pretty good structure when it's all said and done. First off, the first thing you want to do, well, one of the first things is to think about how everything is connected. A lot of what we draw in this class, there's one guy in the middle and everybody's connected to it. That's usually a very good arrangement. There are some rules that will help you decide what should go in the middle, what should not go in the middle. In general, it is the least electronegative atom that's in the center. So the guy that is the least electronegative is usually the one that occupies the center spot. And again, like I said, in most cases, everything else is pretty much attached to it. We never have hydrogen in the middle or fluorine for two obvious reasons. Hydrogen in the middle, as we talked about, would mean that you would have way too many bonds and way too many electrons for hydrogen. And secondly, fluorine should never be in the middle because it is the most electronegative, so that should not occupy it. Really, the most important thing is to count the correct number of valence electrons in the entire molecule. So whatever you're drawing, you want to do a grand total of the number of valence electrons. Number of valence electrons equals the group number. So if we do have something that has a charge, we do need to take that into account. So if something has a negative charge, it means that it has gained electrons and you need to add that to your total. Otherwise, you'll be short electrons. If something is a positively charged ion that we're drawing, you need to subtract the number from your electrons. That way you end up with the correct number of electrons. So positive charge, you need to subtract electrons from your total. Negative charge, you need to add electrons. Again, if it's a -2 charge, you would add 2 electrons. If it's a +1 charge, you would take away 1 electron from your total when you do that. Once you got it arranged and you understand how it should be connected together, first thing you want to do is draw one single covalent bond from the center atom to each of the outside atoms. I personally use lines to do that. So these are bonding electrons, so I draw them as lines. Once you do that, each line represents 2 electrons. So you want to subtract off how many electrons you just used, and you will have leftover electrons at that point. The leftover electrons go on the outside atoms in pairs of dots until each outside atom has the magic number of 8. Unless it's hydrogen, then it should get no dots. Once you fill up all the outside atoms with dots, if you still have electrons that you need to put on your picture, you then go to the center atom and you put it on as dots. At that point, you should hopefully have distributed all your electrons. The last thing you want to do is make sure that everybody has 8 electrons except for hydrogen. They should only have 2. And if somebody does not have 8 electrons at that point, you try to fix the problem by making a double bond. And you try to fix it with making as many double bonds as you need. Once you run out of double bonds, if you still have not hit the octet rule, that is when you should lay up the triple bond. Again, you should not be double bonding or triple bonding right out of the box. It probably will give you not the best picture in that sense. All right, that's a lot of words. Let's do one here together to show how it goes. All right, so we're going to draw NF3. So the first thing we want to do really is we want to count up the total number of valence electrons. Nitrogen is group 5, which means it has 5 valence electrons. Fluorine is group 7, and there's 3 of them, which means it has 7 valence electrons. That is 21 and 5. That looks like a 26 valence electrons, if I'm not mistaken. Between nitrogen and fluorine, the least electronegative is nitrogen, which means it should go in the middle. And fluorine should go around. Again, usually in most cases, not 100% of the time, but in most cases, one thing in the middle, everybody else connected to it. Doesn't matter. I put the fluorine on top. I could put it on the bottom. It doesn't matter. You can put it whichever way you want to go, up or top. Now that I have the total number of valence electrons, this number is super important because when I am done with my picture, I got to hit that number exactly. I cannot have any more electrons, any less electrons. I got to be at that number. I'm going to make one single bond from the center atom to each of the outside atoms. That is 3 bonds. Each line represents 2 electrons. That is 6 electrons I just put on my picture. That means I have 20 more electrons to put on my picture. Yes, 26 minus 6 gives me 20. They go on the outside ones in pairs. So that's going to be 2, 4, 6. That is full. 8, 10, 12, that is full. 14, 16, 18, that is full at this point. I have now placed on my picture 24 electrons. I still have 2 more to go. The last 2 go on the center atom in pairs. There we go. At this point, I have now basically done all my electrons here. I want to make sure that everybody has 8. So if we look at the fluorine on the right, that is 2, 4, 6, and 8. That is 8. All the other fluorines are exactly the same. They all have 8. By the way, you don't have to do these circles, but just to show you. And obviously nitrogen here has 1, 2, 4, 6, and 8 electrons. So they all have 8 electrons. They all meet the octet rule. And obviously it should look something like this before I scribbled all over it. So the correct Lewis structure, again, should look something like that. 26 total electrons. Everybody has 8, and everybody is happy in that case. Any questions on those steps? All right, why don't you try one here? Why don't you try this one here, which is NF3, which we just did. Why don't you try this one? Why don't you try NO3 minus? It might be different from your notes. Why don't you try this one here? Try NO3 minus, see what you come up with. First off, really good place to start is the number of valence electrons. So nitrogen is 5. There are 3 oxygens, each from group 6, which is 6 valence electrons. And we do have a -1. So negative means that we gained electrons. 1 means is how many. So we do need to add this to our total here to make sure we end up with the right number of electrons. So that's 18, 19, 24 valence electrons here are important. In this case, we have 1 nitrogen, 3 oxygens. Also in this situation, you got 1 element and 3 of the same. It's probably that one guy in the middle. Nitrogen is less electronegative. So nitrogen should go in the center. Oxygen should go around. Again, if you want to put the oxygen on the bottom, it doesn't matter. We're going to do our 1 single bond from the inside to all the outside atoms. That has now put 2, 4, 6 off of our total. That leaves us a lot of them out there, but it's at 18, I think, to go. Those are going to go as pairs on the outside. So that's going to go 2, 4, 6, 8, 10, 12, 14, 16, and 18. At this particular point, I have just laid up 24 electrons. Are all the atoms okay here in terms of the octet rule? They are not. The oxygens are good, right? All the oxygens have 8, right? 2, 4, 6, 8. Nitrogen only has 6. So this is a case where we did not meet the octet rule after we distributed our electrons. So we need to fix it. Can I just put some electrons there? I cannot, because now how many electrons do I have? Yeah, I have 26, which is too many, right? So we can't do that. So this is a situation where we're going to make a double bond. So, you might think, well, can I just drop my double bond in there? If I get some ink to right here, there we go. Can I just lay up a disappearing double bond? Try that again. There. Can I do a double bond just like that? I cannot, for the same reason. I now have 26 electrons, and now the oxygen up on top has way too many electrons as well. So we cannot just do the double bond there. So can't just put it here. So what we're going to actually do is we're going to need to take actually a pair of electrons, and we need to move them in to actually make the double bond. Doesn't matter where you do it. It doesn't. I'm going to take a pair of electrons. I'm going to take this pair up here, and I'm going to bring them in to make my double bond. You could actually do it from any oxygen you like in this particular case. When I do that, I will now end up with a double bonded oxygen up on top. Still has those electrons. I will end up with a single bonded oxygen on the right and a single bonded oxygen on the left. And we also usually will put little brackets around it and a charge on the outside because it's an ion when we draw it. Now, when we look at it, the nitrogen has 2, 4, 6, 8 electrons. The oxygen that is single bonded still has 2, 4, 6, 8 electrons. And the double bonded oxygen has 2, 4, 6, 8 electrons. Everybody has 8 electrons. Everybody has used only 24 electrons, and this would be the proper structure here. Question on this one? Now, like I said, you could actually double bond it at any of the oxygens. So if we drew it with the other double bond, say to the left, it would just look like this. Or you could have double bonded it to the right, which you would have looked like this. Any one of these individual pictures would have been sufficient and correct. They are all also related to each other. The only difference is where the double bond is made. These are what are known as resonance structures. Resonance structures occur because you have more than one option as to where you can put the double bond. And basically the real structure is somewhere between all three of those. In this case, the double bond electrons are actually just moving around. There could be at the oxygen on the left at some given point in time. They could be at the oxygen at the top, the guy to the right. They're actually what are referred to as being delocalized, those electrons. And they're basically moving around from any of those parts. If you're not asked to draw resonance structures, you could draw any one of the three pictures would be sufficient. If you're asked to draw resonance structures, technically speaking, you should draw all three of them. Any questions on that? Yeah. Anything that has a charge, we typically, when we draw a Lewis structure for anything that's an ion that has a charge, we put brackets around it and the charge on the outside. Exactly, just write the positive charge. Yeah. So you have to put the oxygen on top, left, right, the one below the nitrogen. Yeah. So if your question is, could we have put the oxygen down here with the nitrogen? Yeah, you could have. It's fine. You could have moved the guy from the top to the bottom. It's perfectly the same structure. It's just turned, so you can do it. Yeah. 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 So if you're asked, I don't know if you'll be asked, but it's occasionally, maybe in 1A, you'll be asked to draw them. But if you're asked to draw resonance structures, you would draw all the combinations of that particular drawing. And basically, for the most part, it's just moving the double bond around to all the possible locations. And you would draw independent sort of pictures for each of those. Yeah. Other questions on that there? All right. Well,